we have essentially a walker which can walk on level ground, and the difference between this one and the passive walker is that there was a slope, and clearly there's no slope. And if there's no slope, then this walker will eventually lose energy and fall down, because it's going to, the foot is hitting the ground, and every time it foot hits the ground, an energy loss. To make up for the energy, it needs to be have some energy supplied to it, and one way of supplying the energy is to have this push off P, which is a ankle push off from the trailing leg. And this is sort of like how humans do a push off with their ankles. So when people walk, they actually do a push off with their trailing leg just as the front foot hits the ground. And they do this pretty much in the single stance, but then they also do a big chunk of it in the double stance. This model doesn't have double stance, so we ignore that, but we assume that that push off is instantaneous, so it's an impulsive push off. So it's just one number which you can put there, and that number, that impulsive push off, will power the walker to make up for the energy loss. There's also a hip torque, and here the hip torque is actually also powering the walking. Now, this problem the problem was here to find the optimal impulse and optimal torque such that it would minimize a cost, which looks like this: p square plus integral t square dt. Velocity and step length is specified, and so if you're doing something of this sort, which I think is kind of challenging, there are a lot of things which go in to get to this point where you're solving this problem. What I suggest is you want to start off with what you have a lot of confidence in, and check your solutions with simple cases, and then build up to the harder and harder ones. And that way also you get some confidence about your solution. So one thing which I gave you was, I gave you the solution, the so-called passive solution, passive hip torque solution. I said that if you put P equals 0.1, and then if you put torque equals 0, then you can find a passive solution. And that is a MATLAB code which I gave you. So the way I would do this is, instead of trying to code this for B, I would try to do part A. In fact, I would go a little bit, I would go sort of, the step before part A is to actually solve the case where you're not doing no minimization. So right now there's a minimization A, but you could do this problem of finding the so-called passive hip swing gait where the cost is nothing. There's no cost to minimize, and you're only finding the passive solution, which you can, by the way, we have done that using fsolve. But the problem in fsolve can also be posed as a fmincon problem by putting cost equal to 0. So you're not optimizing anything. We're just using fmincon as a root finder. So I would actually start off there, solve that problem. There's p equals 0.1, and I'm finding the passive solution, the passive hip solution, which is the same as what I will show you now in a bit in the MATLAB code. Then I would put the torque, okay, and assume P is constant, and then show that the torque equals 0. So you still get that passive solution. And once I have some confidence that that works fine, that's only then will I go to this part B, which is the harder one. But I can tell you that if you do the first two parts, the part B is very simple, because all you do is basically change the allow P to vary. Okay, so that will be the modus operandi. Now I'm going to show you the MATLAB code. Okay, so this is the MATLAB code I provided. It says the same mass parameters. The P is 0.1, and then the once again, let me just check something. P is 0.1, and then slope is 0. And so if you run this, then you get the passive solution. Okay, so the passive solution is basically one with no torque, no hip torque. And then the good thing is that we know something about this solution. It's basically has this fixed point. Okay, so we know that fixed point. And so this particular problem, we used fsolve. Okay, now what I'm going to do is I'm going to try to solve the same problem using fmincon. Okay, there's no optimization. I'm just solving the root finding problem using fmincon, and I think that's bulk of the work will be done there in writing the code. But then that will help us to do part B and C. Now, few things I need to do before I do that, which just will make my life easy. So I know this solution. I'll just copy it down here. Z star equals, okay, and then let me comment this whole thing up. Okay, and so if I run this now, it should work fine. Oh, steps is not defined. Let me just define steps equals 1. FPS dot. Okay, and I really don't need to animate. I just want to get a few things from this solution so that I can use that towards fmincon. Okay, just to make my life easy. So that worked fine. Now within one step, I'm going to do a few things. Now I know that fmincon, I need to figure out what the start state is. I want to figure out what the state before heel's foot strike is, because that will be my optimization variable. I need to know the step time, and so I'll just get all these things a priori from my simulation. That'll just be used to help me code fast. And then I'll of course get rid of that, and I'll just show you it can be done without really knowing that, just to help me code and ensure that I'm coding it right. This will be useful. Okay, so this is this version, I'm just reading the chat, is this version for the OD has been split from foot strike? No, this is basically the code which I provided. So this is the homework 8 code which I provided. It has nothing split, everything is inbuilt. This is basically using fsolve to find the roots. So here what I'm going to do is I'm going to print out a few things. That's the step time. I'm also going to print out the last state 1 through 4. So this is the state before foot strike, and I think that's what I need. So run this now. Okay, so now it gave me a few things, and I'm going to save this, because it will be very handy later on when I give my initial guess. So let's open a new copy. So this is my Z before foot strike, BFS. Okay, and I'm preserving all the 12 digits because that will help me to keep the accuracy. And then this is the step time. Okay, so this is what I should see in my solution. Okay, and then I already copied Z star. So this is my state initially. So that is also Z SS. So that's the start state, right? Okay, temp. Okay, so this will be handy. Okay, now let's start figuring out how to do this with fmincon. Okay, so now what I can do is I actually copied my code for the car shooting one. Okay, I can use that one and just modify that. So let's just do that. So let's call it powered walker fmincon. Okay, this is the file. Close that. Okay, so when I run this, I see that I get the solution for the car problem, right? And then there was one question here, is how do you pass arguments to the f and then to constraints, right? So the other way to do this, which I think I liked, and I don't know why I shifted to this, is to do it this way. So now I'll show you how to pass these arguments to cost as well as this. So you can just copy that, make that additional arguments here, and then get rid of this, pass these arguments as part of fmincon, and then this one, what we'll do is we'll directly put that handle there at cost, and then we'll directly put this handle here at constraints. Okay, and this will also give the same solution. Let's see. You shouldn't complain. Okay, so here is how to do this without actually using this notation. I mean, it's like this one just creates a lot of problems. So now we have it available. Just that I did not use it here, but the same arguments for whatever you pass in fmincon after options are passed to cost and to constraints, and you can use them. Okay, so that's how you take care of that. Okay, now let's think of modifying this code so that it actually gives us what we want. Now, the heart of everything is the simulator. Okay, I need to write the equations here, and then I need to work on the simulator. Okay, the simulator is what I think will basically integrate the equations given the start state, and of course give me the state after end of single stance, and then I can take the foot strike condition and integrate. So I'll do that here. So what I'll do is, instead of making burying everything in the same file, I just think it's much easier if I just put things in separate files. It just will not change anything. So let me just start making copies of various things. So let me copy foot strike. Okay. Well, before I do that, let me just make a folder for this so it's all in one place. Word walker. And then move it, and then this will complain, so I just close this because it's not in that folder. Now reopen it here. Okay, and then let's make this folder here, and so I can just start saving in this folder. So now new file, I've copied foot strike. Let's save it in this folder. Okay, foot strike is done. Next let's move on to see what's the next function. Okay, I do not need the collision here, so I'm going to skip that. Let's look at this one, the single stance. Take this, new, copy, save. Okay, then let's use next. Okay, I think that's about it. I don't think I need anything more. Okay, so we have that, and I don't really need one step. I need to break down that into these two. Okay, so what I'm going to do is, in my powered walker fmincon, I need to rewrite this such that it will have the inputs would be to this would be my start state SS0, and then just state before foot strike and then the time. Okay, so I have already saved that. Let me take that. So I know that these are my solutions, so it's going to make my life easy. So let me copy this here. This is time. Okay, and now since I'm developing this code, I don't want to call fmincon. I'm just going to check my simulator works fine. So let's comment all this out. Okay. Okay, now my simulator is going to be called directly from the main file. I do not need this car file, so just delete that. I would need this, but I need to modify it. So I'll just use it as and when I go. So let's comment it out. Okay, now let's make this simulator take in X, which is going to be my optimization variables, and I'm going to skip this. I don't need those, but I do need to send it in a walker, right? So let me just look at those parameters, which are right here. I need all these parameters, so I'll copy them in here. Okay, so I have that. Now let me call simulator. Okay, so this fellow doesn't like this because, let's see, there's some, oh, it's complaining because the end is missing. Okay, never mind. Now it should be fine. Okay, now this simulator needs X, and what I'm going to do is I'm going to call this function right from here. The call is already there. I need to actually move it down. Okay, so I'll make my X to be First, I will pack in T. Then I would pack the initial state. Let me call that ZSS0 to indicate the state at the start. Okay. Then let's do ZPFS0. Okay. And now when we do the optimization, we'll have additional things like the torque, but right now only this is enough. And then of course P, but let's just keep it like so. Okay, so I'm going to call, well, so this is passed inside this, and now I need to work with this. I go down. Let's pull things up. So that's my X. So first variable is T. ZSS0 is the next 4 variables. So 2, 3, 4, 5. And then Z before foot strike is X 6, 7, 8, 9. Okay. Okay, so what I need to do now is I need to integrate the equations with this initial state and this time. And so I need to go back to powered walker, go to one step and pluck the right call. So I need this part. So take that, paste it in here. Okay, so everything is set here except that I need to specify the time, and I can just go from 0 all the way to capital T, so it takes care of that. The timestamps I don't care, can be, its default is 100, can be 100 is fine. Then I need to, well, single stance T span is fine, Z0. Okay, now what is Z0? It's basically CSS0. Okay, now we can start checking right away, right? So let's see what Z temp end is. Okay, so if everything is right, then Z before foot strike should be the same as Z temp end. We know that. So 1 through 4. Okay, now I'm not sure if this will work fine. Let's see what happens. And then it'll complain because I need to pass these arguments back. So for now, let's just make TT equals nil, ZZ equals nil, mu equals nil. Okay, so if everything right, this should be equal to this one. So I've not, I have uncommented that so that I can reprint it. Okay, that's where it starts. ZBFS0 is undefined. So that's my bad. This will be BFS. Okay, there's a problem. Single stance not found. Okay. I thought I was in the right place. Oh, I've not saved in this place. So I need to go here. I need to move that there. Now it should not complain. Collision is, oh, my bad. So I copied that, but really collision, I'm not using that. So just get rid of that. Okay, so here we have our first sort of victory. We've put in BFS, which we knew from the solution, and the same comes out when we integrate. So that's giving me some confidence that what we did is so far good. Okay, now let's take the foot strike condition. Okay, and paste it here in here. And so this is the state after foot strike. So I'll put ZFS. And here, remember that you can put whatever you want for T end because that really doesn't, T really doesn't figure out there. So you can put 0 if you want. It doesn't really affect. This one is supposed to be the end of that. But since our optimization, we want to use ZBFS, right? Because that's going to be the input. And then we want to see what the output is. So now I'll comment this. This is all checked. If everything works right, then ZSS0 should be the same as ZAFS. Okay, so let's run this again and see if that's right. Okay, so you can see that they're right. So it's another victory. So we've checked this simulator. It's giving the right thing. Okay, so now what we can do is we can ask ourselves, well, we're not change this. So we need to ask ourselves what we need to pass back. So in order to pass something back to the optimization, it's now time for us to actually play with fmincon, since we have already coded the simulator. So let's go to, so this is just checking, check. We need to use this. Okay, so we don't need any of this, delete it. Okay, so we need to put bounds now. Okay, so this is going to be our initial guess. And let's just actually work with this. Okay, now let's see. So we have a cost. In this case, the cost is just going to be 0, right? As I said, we don't really have anything optimized here. We're just doing root finding. Okay. So that's easy. X0 is going to be our initial guess. So let's call this X0. We need A, B, and these can be all like so. We do have some linear constraints, but right now just put everything as non-linear constraints. The constraints are going to be the periodicity constraints here, essentially. Okay, so then we need to give upper bound, lower bound constraints, and then I think we need to pass Walker for sure. Okay, so we have this. Now let's see what we need to put for, let's do the bounds last. Let's work on the constraints first. But just two things are left, bounds and constraints, and we should be ready with this. Options is uncommented. So let's go to this. We have input as Walker. Now here we call the simulator, and that simulator should supply us with well, we actually need to get this also in the constraints because we need it. Okay, so we want, in order for the simulator to work well, we need to return back these things. We needed to return ZFAFS and then ZTempEnd. So we'll call this ZSST to indicate that this is the final state after integrating the equations, and then ZFAFS is fine. So we just need to pass these two, so we don't care about this. So let's just change this to just pack all of it in ZZ and say Z, or you know what, it's easiest if I do it this way, ZSST, and then we can always change this to something different if you think that this is not the best way to represent, but for now I think this is good enough. So it's passed back, this is fine. Okay, so our call will be this, so we make that call here. Okay, and then what my constraints would be, well, the inequality constraints are nothing. There is no inequality constraints. The only equality constraints are now one of them is going to be Z SS0 minus Z AFS should be equal to 0, and then Z SST minus Z P4 strike should be 0. Okay, and we can quickly check this actually. So let's just go here and then check it if it works right. So before we even do this optimization, let's not do it. So let's just check this here. So the X 0, if everything is right, then C equals should all be equal to 0. So why is it printing it twice? That's fine. Oh, because of this. Okay, let's do this again. Okay, there it is. So if you look at C equal to, now it's slightly better. So we have 1 e negative 13, and so everything is pretty much 0 because it's 1 e raised to negative 13. This looks fine. Okay, we got that. Now this works fine. So I think we've done coding constraints. Now this is a matter of using it. Okay, now I need LB.
Can you include those as linear constraints as well?
I did not include the linear constraints are already part of the non-linear constraints.
Right. Okay.
We'll see how that goes. Okay, now we need to give the bounds options in this. Okay, so the bounds now. Right now t is, we know it's 2.44, so let's give a bound between, let's say, 1 and 3. Okay, so, or rather easier if I give it this way: t min is 1, t max is 3. Okay, then I need to give bounds on all my, well, I need to give bounds on this. So z ss upper bound, lower bound, and z ss upper bound. And it's kind of better if you kind of use this ballpark to give the bounds, at least in the beginning, and then you can increase them. So typically what happens is that the system starts with uh, a positive angle, because that angle is the stance leg angle. Let me show you what it is. So it's always good to have this figure. So this is how the leg starts. This is C1 to H is the stance leg, and that angle is positive. Okay, and it will always be positive, because otherwise it will be forward. We always start after foot strike. So this angle has to be positive. So I would give something like, let's say, 0.1 lower bound, 0.3 upper bound. Okay, now if you see this figure again, if this angle leg has to go in the forward direction, then it's positive. It has to go, the velocity has to be negative, because it's going from positive angle to a negative angle. So I need to put a negative value here. So the lower value will be here, let's say point, and so 0.2 cents, you see a ballpark, so it's minus 0.5 and minus 0.1. Okay, and then we need to specify the hip angle. Now, if you look at this figure again, the hip angle is, um, it's actually positive this way when the leg is in front. When we are starting this robot, it's the leg is behind, like in this configuration. So this theta 2 is negative. So I need to give negative values for it to make sense. So I'll put a negative value here. And I recommend here you just give 2 times 0.1, negative 2 times 0.1, and negative 2 times 0.3, just because that angle is always 2 times this, so it just makes it easy. And then the velocity. Now the velocity actually is, there's no reason why this velocity so it can be going forward, it can be going backward. What will happen if it's going backward? It'll slow down, become 0, and then go forward. So you could give negative, positive. I think that a value which is positive would make sense, which makes the velocity go from negative to positive. But let's just give it a range of values. Let's say minus 0.5 to plus 0.5. Okay, it's wrong. Okay, so that completes the state for SS. Now let's do the state for BFS. BFS, LB, C, BFS, UB equals. Okay, so let's start populating it. Now the good thing about this is it's basically a mirror image. Okay, the angle is, if the angle is like so, it's going to be the negative of that. So what we can do is, for the positions, the angles, we can just give the negative or whatever we specified. So we can just give minus, so minus 0.1 and minus 0.3, but minus 0.1 is going to be the upper bound, and minus 0.1 is the lower bound, because minus 1 is numerically greater than minus 0.3. Okay, now the velocity, it turns out the velocity cannot change. It's going to be negative, it's going to remain negative, it can't go positive. So I need to still give a negative velocity. So that velocity, let's just put the same thing. I think I swapped it here. Lower bound should be minus 0.1, upper bound should be minus 0.5. Okay, minus 0.5, minus 0.1, and then we can give the same thing here, minus 2 times 0.3. I think this will complain, because negative 0.6 is smaller than 2. Okay, that's fine. And then we can give same thing here. Okay, so that's initial guess. Okay, I think we are all set here. So we just give the lower bound to be z ss lb z bfs lb z um, SSUP Z PF Okay, now if I play this and everything is fine, the solution is already there, so it will just give me that solution. Okay, so there's something wrong. Uh, Too many input arguments. Okay. Okay, let's see this. We have 4, 4, T min, T max. So there's something about the number of arguments here. Okay, let me see this. Your initial x-ray is not between the bounds. Interesting. Let's see why that's true. So t is within the bounds. ZSS 0.18, that's in bound. Minus 0.27, that's in bounds. Minus 0.36, oh, this is not in, oh, that's in bounds. Minus 0.5, that's fine. This is all in bounds. Maybe the second one. Minus 0.3, this is in bounds. Minus 0.27, that's in bounds. 0.36, now this is not in bounds. Okay. Oh yeah, this should be positive because the angle always goes from negative to positive. So this should always be negative of that. And then the last one should be fine. So I think I fixed that, but I still did not fix this. Too many input arguments. Okay. This will not run. One lower bound exceeds the upper bound. Oh, this is the problem. 0.1, 0.3. Okay. Too many. Okay, I fixed that problem now. This is a problem which I've not fixed yet. Too many input arguments. Help fmincon. Okay, this is what then fun x0 a b equals b equal lb constraints. That looks fine. It's not this.
You might be passing Walker in the cost function or the constraints. Oh yeah, in the constraints.
I can pass it here, but that should be fine. This syntax works. I checked it. Constraints. Oh, okay, so that was the problem. It was basically that I had to always say Walker, otherwise it doesn't work. Okay, okay, so here it converged and it says that whatever I had was actually the solution, which is clearly means that it's good news, but it's not how programs work, right? We don't normally hit the solution. So let me just put a random guess and see if we get this solution. So we know that the solution is this, but let me just give a random guess. T equals to ZSS equals 0.15 minus 0.2 minus 0.30. So that's for the state before fifth strike, and then sorry, in single stance, and then I have 0.15. Let's just give minus 0.15, minus 0.2, 0.3, and 0. Okay, and my x0 now is t z 0 c pfs. Okay, now let's see if this works, and I'm going to print this out. Okay, so that's the solution, I know. And then let's compare x with x, I can call it x solution. Okay, this is really hard to see. Let's just make it this way. Okay, so here is this is the solution which fmincon gave, and this is the solution which I have. Now the question is this the right solution? And this is where I can use my powered walker to check. So all I need for the powered walker is to give the initial three states, these three states, 1, 2, 3, 4, sorry, four states, 1, 2, 3, 4, and that. So I know, so something which I probably mention is these passive walking models usually have two solutions at a given p or a given slope. One solution is usually the stable one, the other one is the unstable one. My hunch is that it is actually giving me the unstable solution. So I can say just copy, paste in powered walker.m. What I need to paste is disk x1 through 2 to 5. So run this now. Okay, so I need to take this and paste it in here. Yeah, so let's see what happens if I, so once this goes in, I wanted to print z end 1 through 4, right? That's the last 4 states. So that's that. See if we get the same thing. Okay, so what you can do is now see if this value is the same as, it's not right. This one looks close, but it's not quite there. 0.249, 0.25, 0.0. So it is not, it's not a periodic value as far as I can see. It's close, but it's not quite there. It's kind of close to that one. Okay, so this kind did not give the solution. Let's go back here on it. And then let's just print the exit flag. Fval exit flag. Okay, so exit flag fval is 0. Local minimum is found. Okay, let me check this. I'm going to go and check with constraints. So we have this, and let's look at x, right? And so see if c is true. So you can see it's 1e negative 15, and so it looks like it meets all the constraints. Okay. However, it doesn't look periodic to me. We can do an animation now to see if that's what we expect. Okay, it looks pretty good, but it doesn't really give me a periodic solution, as you can see here, 0.215. Okay, so one thing which I missed in this, and I think this might be the reason why it's not really giving me a periodic solution, is remember I got rid of, well, I got rid of this, well, I took this collision, I got rid of the collision condition, but I really didn't put it anywhere. And so, how does my optimization even know that there's a collision, that is the legs obey that angle, right? So I need to put that into my formulation, and I did not do that. So if you look at the collision condition, collision, it basically is specifying how exactly these angles should be just before foot strike, right? Before foot strike, theta 2 should be twice theta 1, and I need to put that. So let me go to here, and then I need to put in the constraints. So I need that one, and so that condition is basically, so I need to get theta 2 before foot strike, right? That's something. And then theta 1 before foot strike is something else. So that comes from this PFS. So that should be the third value, and this, the first is theta 1 should be the first value. Okay, so collision condition, this is basically saying that it should be a isosceles triangle at collision. So this is PFS. Okay, and this should be another condition. Okay, now let's run this. Okay, so we got a different solution this time. Let me make it print this. Okay, take this, take it here, and paste it right here. Okay, and let's see what it gives. Okay, now if we look at, if you compare this one, this is after integrating one step, applying the collision. You can see that it is exactly the same as this. So what we've done here is we actually found a different solution. This is not the original passive solution. And as I said, these models have two solutions. This one is probably the unstable solution. Okay, and you can check the eigenvalues. So we actually found the unstable solution here, though, even though we did not start off that. You can actually, if you want to find the stable solution, you can try playing with this. Maybe put 3 and let's see what happens. Okay, now I think it gave me the stable solution. See this 0.183, as this 0.277, 0.367. Okay, so this one gave me the stable solution. Just changing the time gave me that. Okay, so this is we've basically succeeded in finding the passive solution, which had a cost of 0. Okay, I can delete the other things. I don't need them here. Just let them just be there. Okay, so that's the first step. So by now coding this, writing this code, I've basically done the same thing I do with fsolve, but now I've used fmincon, and that gives me some confidence that all my equations are right. The next step would be to actually do this problems now, these two problems. So what I will do is I still would like you to try, and else I can do it next time. I will provide this code to you now that I've taken the fsolve problem and done it in fmincon. What you would have to do now is put t square in the code. So one more optimization variable now would be the torque. Maybe this is a bad choice for F, but capital T. So you can make U as the, I think this will be confusing. Let me just make it uh, time. That way it's not confusing. And so it doesn't really affect your notation. Time min, time max. Change it everywhere. Okay, let's check if it works. Nope. This is line 24. Hmm. Okay. Okay, works like usual. Okay, so this is now working now. So what your goal is next is to, I mean, you can use your code if you think you've reached far enough. You don't need to use my code. But the next step would be for you to try. Let's see, where is that? Okay, so what I want you to do now is work on part A and part B. For part A, don't change P. Okay, keep it fixed. Don't introduce that as an optimization variable. Just introduce the torque as the optimization variable. Put the torque as one of the decision variables here. Torque equals. What you'll have to do then is go to cost, add torque square dt, and then you will have to put, when you do this simulator thing, you need to integrate this from one grid point to another grid point. So this, just note how I did it in my original file. I think I closed it. So you basically you need to integrate from one grid point to another. So when you have torques spread over time, you have n grid points, right? So you need to go from integrate from one grid point to another grid point. So you will have a for loop here. Needs a for loop for torque. Okay, and then that torque will go in. It will be modified inside single stance. Here it will be there, the torque, and then you should be able to first solve for this one. And so you should find that the solution for that problem is that torque will be 0, and you'll get the same passive solution. If you get the same passive solution, it means that you have some confidence over your optimization. Once you do that, then go to the second part, which is basically now introduce p square, introduce t, but introduce t as another decision variable, put a velocity and step length constraint, and then see if you can basically find the solutions for that step length and velocity. Now, this is something which I forgot to include here is when things go very fast, when this walker goes very fast, there's a potential there will be a flight phase. So there's a condition in which the force from the ground on the leg becomes less than 0. If it becomes less than 0, then the leg is sucking on and not the ground is sucking to on the leg or not pushing it, and that condition has to be ignored. And that's actually in the equation. So this is kind of safe zone, but if you are doing a simulation where you're looking at fast walking, then you want to put that condition. That will show up as a inequality constraint, that C, which is in constraints, and then that should take care of that. But okay, so the goal is to do this now that I have this code, and I'll post this video. And once you do that, hopefully you'll get the answers, or else I can do it in the class next time. Okay, so let's do one thing. Let's take a
Professor?
5-minute, question.
Oh, I just had a quick question. It's actually on the area of code we're looking at currently about the for loop. This is one of the things I was curious about. So in this instance of the code on screen, we would be integrating between the bins of t-span, correct?
Right.
Okay, so it'd be like t-span 0 to
So
0.1.
yeah, so you need to do this.
Right, okay.
So do this, t-span equals linspace 0 time n plus 1. So you have n grid points, so you have n plus 1 spaces between them, and the torque is basically different between each of those grid points. Yeah.
Okay,